Yes, there are no neutrinos. Well, when you hear that statement, you might throw up your hands and say, well, that's nonsense. Of course neutrinos exist. And then you add, well, we need neutrinos to conserve energy and spin angular momentum from beta decay. But I suggest you read this first before you reject my statement. Unless you understand a new and different formulation of spin, you will not understand why neutrinos do not exist. Now I'm suggesting that the standard model needs to change the weak force from SU2 to the quaternion group Q8. Notice theorem says we can do this. There is nothing wrong in changing the symmetry and finding new conservation laws and properties, so there can be no objection to it. Changing symmetry may lead to nonsense, or it may lead to sense. We only know when we try. Q-spin makes a lot of sense and answers many questions. It is easy to change the symmetry to the quaternion group. All you do is multiply one of the Pauli spin operators by the imaginary number I. That is all you do, and then you follow the logic. The basis for Q-spin is on the same mathematical footing as the Dirac equation and the firm footing of quantum field theory treatment of spin. And from this small change of multiplying by I, almost everything you know about the microscopic changes. Under the quaternion group, a fermion spin of 1/2 is actually incomplete. It only describes the particle nature of spin and not its wave nature. The complementary property of spin has not yet been formulated. It is the helicity, which is coherence and gives wave nature to spin. Q-spin adds helicity by introducing a bivector, I sigma 2. This is the main point of this work, adding in the bivector. The Dirac equation has no bivector, so we need to include it, and that makes all the difference. This is how you view spin. Universally, a spin 1/2 is viewed as a point particle of intrinsic angular momentum, a vector operator with two polarized states, like a bar magnet north and south, with spin up and spin down. And n is a vector on the Bloch sphere. The spin you know is fully described by the Pauli spin vector sigma. However, this is only the particle nature of spin. What about the wave nature? Q-spin has structure and is a spinning disk of angular momentum. The magnetic component is orthogonal to the direction of motion, which is spun by a unit quaternion. This is not a fermion of spin 1/2, but a boson of spin 1 in free flight. As now shown, the boson results from the coupling of two spin 1/2 axes to give the resultant of 1/2 plus 1/2 spin equals 1. Quaternion spin has structure which is geometrically identical to a photon in free flight. This is totally different from what you are used to. It means that qubits, for example, disappear in free flight with implications to quantum computing. On the right gives a more detailed view of the Q-spin, showing the spinning axis of linear momentum and the two orthogonal components of spin angular momentum, sigma 1 and sigma 3. They form the plane of a spinning disk. And these two spin angular momentum, sigma 1 and sigma 3, can couple to give the boson of spin 1. Here is some motivation regarding the bivector. This well-known formula from geometric algebra shows that the geometric product of two Pauli spin components gives a symmetric term, which describes the polarization, and a bivector term, which is antisymmetric, and this describes coherence. Look up Pauli matrices in Wikipedia to see this. Under the usual SU2 symmetry, there is no bivector in Minkowski spacetime. Usual spin is a point particle vector quantity described by the three Pauli matrices sigma x, sigma y, and sigma z. Quaternion spin introduces the bivector, So we have two spatial axes, sigma 3 and sigma 1, and the bivector, that is the axis that spins. This axis, as I show, spins due to a uniquaternion, which formulates the helicity. Although helicity is used in elementary particle physics, it is different, simply measuring the helicity but not formulating it. We formulate the helicity as the complementary property to spin polarization. Helicity is a second-rank, totally antisymmetric property, that is the contraction between the Levi-Civita tensor and the bivector. This defines the complementary property to spin polarization. Note the geometric product is complementary, since the symmetric and antisymmetric contributions cannot be manifest simultaneously. Define Q-spin as the sum of the symmetric polarization and the antisymmetric helicity. This is a vector on the Bloch sphere too, but now it is a spinning vector around the n-axis. Let's look at the differences. Without a bivector, the Dirac equation cannot formulate the helicity. But under the quaternion group, it can. And this simple change does a remarkable thing. It finds the complementary space and property to spin polarization. To get the bivector, just multiply one of the gamma matrices by the imaginary number I, and I choose gamma 2. And then it becomes Hermitian. Here is gamma 2. Note that the SU2 Dirac field is in Minkowski spacetime, but for the structured spin, we need a body-fixed frame for each spin because every spin can be oriented differently. The subscript S denotes the body-fixed frame of a structured spin. Note that immediately the signature of the spin spacetime, subscript S, is changed. Rather than under SU2 with a signature of 1, -1, -1, and -1 in Minkowski spacetime, that is, 1 time and 3 spatial components, we have in contrast 1, -1, -1, +1 for spin spacetime. 2 spatial components, and now the 2 is a time, or a frequency. I order the 3 components as 0, 1, 3, and 2. With this change to the quaternion group, 2 becomes a time and defines the spinning of the axis. That is the frequency. Frequency depends upon the angle. Angle and angular momentum are complementary elements of reality. Now this is quite different and more complicated than the point particle spin, but there is a lot more. Consider first in free flight, spin is in an isotropic environment. Then there is no difference between the 1 and 3 axis labels. We can switch them without changing the equation. Let us choose a permutation operator, which is a parity operator, permutation P13, and apply it to the Dirac equation now with the bivector. P13 just interchanges the 1 and 3 with no net change to the equation, but the bivector is odd to this permutation. Note that operating P13 on the bivector swaps sigma 1 and sigma 3, which means it is minus sigma 3, sigma 1. This means the quaternion Dirac equation, or Q-Dirac, is non-Hermitian, and it has 2 forms which are Hermitian conjugates of each other. The 2 forms describe left and right helicity, eventually. Hence, P13 changes the sign as seen and gives 2 states that have no parity. That is, P13 operating on psi plus or psi minus gives psi minus, psi plus. The permutation gives 2 reflective or mirror states, as seen in the figure. You can see that the sign change means that psi plus is in a right-handed frame and psi minus is in a left-handed frame. Also note that when you add psi plus to psi minus, that the imaginary axis cancels, leaving only the sigma 1 and sigma 3 components. If you subtract them, then the sigma 1 and sigma 3 terms cancel, leaving only the imaginary axis. The point here, then, is in free flight, The Q-Dirac equation has two solutions which are mirror states. All we do is follow the logic after making the symmetry change, and this slide is crucial. We find the complementary space to spin polarization. And this is quite a big change from our usual point-particle description of a spin. In the last slide, I showed that quaternion-Dirac equation describes states of no fixed parity and are mirror states, one from the other. I mentioned that P13 is a parity operator, and that, since the spin is in an isotropic environment, but the 1,3 axes can be interchanged without changing the equation. However, the bivector is odd to parity. Here we see that P13 changes the left out to right-handed states and changes one state to its mirror image. Let me take the sum and difference of the two mirror states. Immediately we see that under parity, the addition is even to parity and the subtraction is odd to parity. We now have states of fixed parity. Doing this means we can add and subtract the two forms of the Q-Dirac equation, and in doing this, as seen from the figure, adding gives a two-dimensional Dirac equation in spin spacetime, and subtracting gives the equation for a massless Weyl spinner. We have found that spin spacetime breaks up into two distinct and complementary spaces. A 2D spacetime with components 0, 1, 3, and a space, not a spacetime, for the two axes. In the next slide, the two equations are solved. The 2D Dirac equation gives a disk, a plane formed from sigma 1 and sigma 3, and the Weyl equation solves to give a unit quaternion. Quaternions exist with four spatial components called the S3 hypersphere. This, then, is helicity space, and the quaternion spins the axis. That's all it does. Although we cannot observe the quaternion, we observe its effect in our spacetime, and that is, spin is a spinning disk. There are two complementary spaces of a spin 1/2. These are analogous to the Fourier and inverse Fourier spaces of position, momentum, and energy time. We have found the complementary property of polarized spin in a space beyond our spacetime. A real physical attribute of spin, that is, how it spins, exists beyond our visualization, beyond our ability to measure, but is nonetheless an element of physical reality. Let's say this in another way. Here are the complementary properties that you know well: position and momentum, energy time, and angular momentum and angle. People erroneously believe that the complementary property of angular momentum are two non-commuting components given here. But the commutator is different from the angular momentum angle above here. Also, we need one angular momentum property and one angle-dependent property. The complementary property to spin angular momentum is the spin helicity. These properties are complementary. These properties are simply incompatible because they do not commute, and the Heisenberg uncertainty principle follows. Spin spacetime separates into a two-dimensional Dirac equation, the disk, and a quaternion on the S3 hypersphere that spins the disk. Here I depict the relationship between the various spaces: Minkowski spacetime, which is our dimension; spin spacetime, which is the 2D disk, that is spun by the unit quaternion from the S3 hypersphere, shown here. All we see of S3 quaternion is the spinning axis and its projection onto Minkowski spacetime. The solution to the two-dimensional Dirac equation is identical to the usual three-dimensional Dirac equation, except in 2 dimensions. It gives the same form in both cases as seen by the 2x2 matrix, and the energy is the same except the two momentum terms are due to the internal structure of the two-dimensional spin. Here is a great departure from Dirac, who also got two mirror states with the same energies, one positive and the other negative. After a lot of thought, he came up with the idea of a matter-antimatter pair, but this caused a problem with the negative energies. He constructed a fermion continuum and filled it with electrons, giving a sea of electron model and hole theory. Q-spin is prosaic in comparison to the matter-antimatter pair. Rather, Q-spin has two axes that are mirror states, and these spin oppositely, one with positive energy and one with negative energy, which just balance each other. Q-spin resolves the negative energy problem that Dirac struggled with. The figure here shows Q-spin in the middle part being the coupling of the two fermion axes to form the boson of spin 1. However, as the free flight moves into an anisotropic environment, the boson uncouples so one axis aligns with the filter direction and the other averages away at right angles to it. A fermion is formed from either sigma 1 or sigma 3. Notice that the 1 and 3 axes have opposite magnetic moments. In the other figure of the free flight boson, just to confirm the relationship between the three axes, the sigma 1 and sigma 3 and I sigma 2 are the same in this diagram as in the coupled diagram here, which shows the boson and its two fermion components. Note also that even though a spin 1 boson is formed, the helicity spins the axis so fast that it averages the angular momentum to 0. Even though the boson spin is present, it displays no angular momentum in free flight. In free flight, we only have the helicity. In the next 3 slides, I show the decoupling of the boson to one of the fermions. The decoupling depends upon two things. First, the strength of the field relative to the spin-spin coupling that couples the two axes to give the boson. Second is the orientation of the boson relative to the filter. Here I have drawn in a filter, and note that the spinning disk of spin angular momentum is coplanar to the filter, not parallel to the direction of motion as usually stated. The filter angle A and the orientation of the coupled spin sigma 1,3 is shown. The spin sigma 1,3 is pulled to align with the filter direction A, but it depends upon how far the boson is from the filter. There are two mechanisms. If the field is far from the boson and closer to one of the fermionic axes, that axis will break away from the boson and it decouples. In this case, sigma 3 is closer, so it aligns, and we have a transition from a boson to a fermion. This is the principle of least action. The field can also be closer to the sigma 1 axis, and then it aligns with the field direction, and the boson decouples into a fermion. The sigma 3 axis averages away by spinning perpendicular to the aligned spin axis sigma 1. If the filter is closer to the coupled boson, it will process as a spin 1 and not immediately decouple. It is shown here. We assert this will happen when sigma 1,3 lies within 22.5 degrees on either side of the filter. Then the boson spins as a spin 1. Note that the boson has a magnetic moment of 2 mu, so its Larmor precession frequency is twice that of the fermions. Now eventually the boson will decouple, and the fermion axis that lines up will be the one that is closer to the filter. It is an example again of least action. The closer spin aligns. Since sigma 1 and sigma 3 have opposite spins, it is important to know which one aligns. This then is the transition from a free flight boson to an aligned fermion. There is nothing new about this. Spectroscopy is replete with such situations, and they are well understood. Let's use the fact that spin in free flight is a boson, and when measured it is a fermion. Therefore, for beta decay with fermion electrons, the antineutrino is introduced to balance the spin. That is, introduces a massless fermion. Beta decay with Q-spin, however, is a boson, so the neutrino must be spinless. Let's call it naked. Another reason for introducing neutrinos was to conserve the energy distribution the point particle Fermi electrons failed to do. Q-spin has internal structure, and the internal energy in free flight is due to the helicity, and the energy can vary with the frequency of the helicity. Q-spin accounts for both the conservation of energy and the conservation of spin without the need of neutrinos. We find the properties of a neutrino, that is, a fermion with helicity, are exactly the same properties as carried by Q-spin. The boson of spin 1 obviates the need for neutrinos to be fermions, leaving only the helicity. Neutrinos are mistaken for helicity. Hence, neutrinos do not exist and are not needed in Q-spin theory. What about all the experimental evidence for neutrinos? No neutrino has been directly detected. Detection relies on collisions with other particles, but the collision cross-section is so small that neutrinos hardly ever collide with anything, and so they hardly ever react. The removal of neutrinos by collision reactions is negligible compared to the enormous rate of production. Therefore, once produced, they have no purpose and simply fill the universe with antineutrinos, assuming, of course, that the relatively small numbers of neutrinos are annihilated. All particles in nature seem to have a purpose. Once produced, they go on to do other stuff. Neutrinos do not, or if they do so in negligible amounts. Neutrinos have no role other than to balance the energy and spin in beta decay, which Q-spin does without neutrinos. After they are produced, neutrinos seem to be useless. If they go on to do nothing, eventually the whole universe will be full of antineutrinos. Over the 14 billion years of production by now, the numbers must be enormous, rattling around the universe, and the numbers will keep on growing unchecked as long as the suns do shine. The second reason against neutrinos is that, as I said, Q-spin can balance the energy and spin without them, so neutrinos are not needed. Experiments claim that neutrinos are detected, but you be the judge. The Super Kamiokande, with 50,000 tons of pure water and 11,000 photomultiplier tubes, all 1 kilometer underground. It cost US dollars 600 million to build in 1996 dollars. A typical experiment had a total flux estimate of 10 to the 57 neutrinos, and in that experiment, only 19 neutrinos were said to be detected. To repeat, over many years, 19 out of 10 to the 57. There are only 10 to the 23rd stars in the whole universe. I find it very hard to accept this as conclusive evidence for the existence of neutrinos, specifically since I have a reasonable alternate explanation. That is, in my opinion, their initial was believing the beta electron was the usual Dirac fermion spin, rather than the boson Q spin. This convinced the physicists that neutrinos must exist. To learn about the current view of neutrinos, look up James Riordan's book or his YouTube video, The Ghost Particle, Searching for the Mysterious Neutrino. As I said, he wrote the book on neutrinos, and his lectures are clear and thorough. One point that struck me was the amount of speculation and conclusions drawn from either no or scant experimental confirmation. He also promoted neutrinos as the new photons that could be used in astronomy and communication. Neutrinos, I suggest, must be relegated to the journal of wrong ideas. Q-spin changes a lot of our understanding of nature. That quaternion spin shows that neutrons do not exist makes a lot more sense than the current view of billions of neutrinos flying around doing nothing and accumulating ad infinitum. Neutrinos have no purpose other than to fill up the universe with non-interacting, useless particles. Their only role is to balance angular momentum and energy and Q spin does this nicely in its boson form. So the conclusion is that, yes, there are no neutrinos.